Okie doke. So on to 8-4. So we're going to take a look at adding and subtracting now. So we're working our way through. We did simplifying radicals. Now we're going to look at adding and subtracting. And to be able to do that, I want to do some review warm-up questions, some things that might pop up, and just to double check on a few things. So first of all, way back from chapter 1, how do we add fractions or subtract them? We need to get a common denominator. So we have these warm-ups up at the top here. So what would your common denominator be? What is a number that both 5 and 4 divide into evenly? Both of those could be 20ths, right? So let's see if we can make these each into 20ths. So what would you multiply the first fraction by to make a 20 from a 5? Well, you'd multiply by 4. Remember, you have to multiply the numerator by 4 as well, because we can't just multiply the bottom by 4. We're multiplying by something that's equivalent to 1, 4 over 4. So completely legal to do, and we got to make sure we do it in the top and the bottom. So same argument here. To make a 4 into a 20, we multiply by 5, but then also the numerator as well. So 15 20ths. And then we can add together. So 4 plus 15 would be 19, and then 20ths. We're trying to see how many 20ths we have. So part of what we're going to do today, we are going to need to do some common denominator. All right, second one, like terms. Let's talk about what's like and what's not. That's going to be an issue for us too today when we talk about adding and subtracting. What can we put together? What about the middle one here? We have an x and an x squared. To be like terms, same variable with the same power. This is already simplified. So something to be looking for, sometimes you can't do anything. And that's okay. In this case, we can't because they are not alike, because one of them has a squared, the other one doesn't. How about the next one, though? They're both just x to the first. Totally fine. How do we put them together? We do the operation with their coefficients. So we have -5 minus 7 more would be minus 12 of them. So these same exact rules that we just talked about are what we're going to do today with adding and subtracting for roots and radicals. So putting together those coefficients, all those things very much the same. So how do we add and subtract? All right, so the big important thing to recognize is the only radical expressions that have the same index, so that's like the root, and the same radicand, love that word, that's the stuff underneath, may be combined. So that means you have to have the same root, so that's the index, and the same expression underneath. So the same expression underneath the radical, that's called the radicand, love that word, in order to be able to put them together. So for example, if you take a look at these two, they are not alike because the stuff underneath is different. That's not a like term. So the radicand is different. So just like having kind of like an x and a y, if you're trying to add together a 5x plus a 2y, you wouldn't be able to do that either. So square root of 3 and square root of 2 are just like having an x and a y. The radicand is different. Okay, so what's the issue with this one? Why can't we put these together? They both have a 3 underneath. Well, that's a cube root. This one's a square root. Those are called the index values. The indices are different. They're not the same root. So like saying the square root of 3 versus the cube root of 3, those are different numbers, right? If we did them on our calculator, not the same thing. So in order to be like terms, so we talk about what it means to be alike for radicals, same root, same expression. So the fancy mathematical term for that is index and radicand. So same root, same stuff underneath. All right, so let's practice a few of these and see what we can come up with. All right, so first one, I see 3 square root of 5 plus 7 square root of 5. So they're both square roots, yay, and the expression underneath, the radicand, is the same. These are definitely like terms. Now, how do we put like terms together? I'm going to write a different problem here. What if I just said, hey, can you do 3x plus 7x for me? What would you do? Well, you would say, I'm going to put the 3 and the 7 together, and I'm going to call that 10x. This is identical. I'm going to add the coefficients, so it's asking me to add them. So if I have 3 of these square root of 5s plus 7 more, that's going to give me 10 of those square root of 5. So it's exactly like what we do if it's just a variable term. It's the same idea. So I'm going to do the same sort of thing when I add those radicals together. All right, let's take a look at the next one. I can have more than one term sometimes, so if I'm looking at this one, I'm feeling pretty confident about these first two. What's the coefficient in front of that just 11 if it's not written? It's a 1, yeah, so just be careful on that. But 44 isn't alike. This is different. But here's the thing. We have to simplify these radicals first and see if we can break them down because they might become like terms if I do that. So that's why we spent that time breaking down and simplifying radicals so we would be able to do this. So let's take a look and see if we can do something with this. The coefficient's still going to be 3, but can I write 44 as a product? So remember our product property, right? The product, the square root of a times b is the same as the square root of a times the square root of b. So is there a perfect square that divides into 44 evenly? Well, sure thing. What about 4? 4 times 11. I can break it down. So why this is so awesome, now take a look at what I can do. Square root of 4 is 2. This is a product. The coefficient is multiplied up front, so don't forget that. We have a 3 then times what's the square root of 4? 2 times the square root of 11. So that gives me a grand total of 3 times 2, 6 of these square roots of 11. Now, why was that such a big deal to do first? Well, now take a look at what we have. I have 3 terms that are all square root of 11. So because I simplified, I realized that all of these are like terms and I can put them all together. So I have 2 of them minus 1 of them plus 6 of them. So 2 minus 1 would be 1 plus 6 would give me 7 times the square root of 11. So the key thing here is always simplify first. See if you can break things down so you can put them together. So that's a really big idea for when we deal with doing operations with radicals like adding and subtracting. We have to make sure we simplify them first. The harder the radical, the more work we might have to do to take care of that. All right, let's take a look at the next one here. So we have 9 times the square root of 5 minus 4 square root of 10. Now, if we take a look at this one, square root of 10 and square root of 5 are not the same, so the radicand is different. Can you simplify either of those? Well, are there any perfect squares that divide evenly into 10? Well, 4 doesn't, 9 doesn't, and then you're already too big. Same thing for 5. Can't break either of them down. These are not like terms. You can't put them together. This one is already simplified. I know it seems like you want to be able to do something, but you can't if the radical is different. So different indices, different radicand, or maybe both, we can't put them together. So nothing we can do on that one because we can't simplify. All right, let's take a look at the next one. All right, so we have this expression right here. So this is the actual expression. They're telling you this off to the side. Let's just talk about that for a second. It says y has to be greater than or equal to 0 because y is under the radical. Remember, you can't take the square root of a negative number and get a real answer. So they're just telling you over here something about the domain, what you can use. Just make sure that your y values are positive. So this statement only makes sense if we use positive values for y. That's what they're saying over there. All right, so are these like terms as they stand right now? Nope. Different radicands, different expressions underneath, but I don't think either of them are simplified. So what we're going to do is we're going to go ahead and see if we can break each of these down into a product. All right, so let's think about 12. 12 isn't a perfect square, but what's the biggest perfect square that divides in there evenly? So think about your perfect square list. I'll write it down here again. So we have at least a few first ones here. 4 divides into 12, right? So we'd have 4 times 3. And then y. Is y a perfect square? So remember how we double check. The indice has to be bigger than what the square root is. And it's not. The power isn't bigger than the indice there. So I can't take one thing and break it into 2 groups evenly, right? So y is not a perfect square. So I'm going to go ahead and put it with what I can't do. All right, 75, same conversation. Go up your list here. Do any of these numbers divide into 75 evenly? How about 25? 25 times 3? Awesome, that's looking really good. So I had a 3 over there. And again, same deal with the y. Y to the first can't be broken up into 2 groups. It's only one of them. So we have a y to the first left over. All right, so I'm thinking pretty positively about this. I think we're going to be able to break this down. But we need to do that work first. So let's do the square roots that we can. So square root of 4 is 2. Remember, this is a product. So that means 5 times 2 times the square root of 3y. So 5 times 2 would be 10 times the square root of 3y. Plus, we have 6 times square root of 25 is 5 times the square root of 3y. So 6 times 5 would be 30 times the square root of 3y. So notice I simplify each part. Now I can take a look and say, okay, do I think these are like radicals? They have the same radicand, same expression underneath, and they're both square roots. Life is good. I can put these together. They are considered alike. How do I put them together? I combine their coefficients. So 10 of them plus 30 of them gives me 40 of these square roots of 3y. So I can put them together. They are like terms because I simplified first. So if I hadn't simplified, I never would have been able to see that. I would have stopped. So make sure you always simplify first. Okay, now we're gonna go up in indices here. We're gonna try other roots besides square roots. That's kind of the difference we're doing more of in Algebra 3 than what you did in Algebra 2. I'm trying to deal with these higher powers. So you really need to look at your list of your perfect force in this case, and double check to try to help you out. As of right now, those are not the same number. I would be completely out of luck. But what we're gonna try to do is see if we can write this as a product. And same thing here with 162. Are there any perfect force that would divide into these numbers evenly? Let's start with the 32. Okay, so 32, let's do our perfect force. So 2 to the 4th is 16, 3 to the 4th is 81, and then I don't even think we need anything bigger. So does the 16 divide into 32? Sure does. 16 times 2. And then let's try 162. Does 16 divide into 162? I don't think so, but does 81 divide into 162? Sure does. How many times? 2. Just go up the line. Just start on your perfect fourth list and just start dividing the numbers by those perfect fours. Find the biggest one that divides in there evenly. All right, why does this help us? Well, now I can do those fourth roots. So remember this -2. This is a product, right? These three things multiplied together. The fourth root of 16, what times itself 4 times gives you 16? Well, 2. A lot of 2's here. So -2 times 2 would be -4 times the fourth root of 2. That's as far as I can go on that one. Next one, still a product. I have a -7. Let's do the fourth root of 81. So what times itself 3 times gives you 81? Well, that's 3. And then times the fourth root of 2. So 7 times 3 would be -21 times the fourth root of 2. So all the way through here, we're trying to figure out, are these like radicals? So we're trying to simplify first. Let's see if they're the same. They both have a 2 underneath, so same radicand, and they each have the same indice. They're both fourth, so we're good to go. We can put together their coefficients. So -4 minus 21 would be -25 times the fourth root of 2. So I was able to simplify it all the way down to that. So the idea is we try to simplify. Maybe they won't be the same, and that's okay. But if they are, sweet, I can put them together. All right, let's try a cube root. So we're just trying to find different things, and now we're going to use some variables as well. This can be hard for people. So if there's no numbers, numbers are a little bit more reassuring because I can look at the list. So we're doing perfect cubes. These are definitely not the same. So let's see if we can simplify this first one, what I can take the cube root of and what I can't. 4 does not divide into 3 groups evenly at all. So remember how we did this. It's 1 less than, because it's the first number less than 4 that's divisible by 3. So p cubed times p to the first, because 3 divided by 3 is a perfect cube, but 3 times 1 gets me back to that 4, so I can have my perfect cube. All right, 7 doesn't divide into, or 7 isn't divisible by 3 either, so I can't take 7 cubes and divide it into 3 groups, but what's the closest number to 7 that is divisible by 3? Well, can I do 6? Is 6 divisible by 3? Sure is, so that's going to leave me with a q to the first left over as well, so I can actually break it down. All right, the second one, cube root again, we're going to see if we can break this one down, is 64 a perfect cube? Double check your list. It most definitely is, so 64 is fine. P and Q, there's only one of them. That power is less than the indice. There's no way to take one thing and divide it into 3 groups, so neither one of those are. Now that makes me feel pretty good though, because I think that's going to look like a like term then. All right, so let's go ahead and do the roots here. So the cube root of p to the third. So 3 things divided into 3 groups. How many in each group? 3 divided by 3 would be p to the first. Q to the 6. 6 things divided into 3 groups. So 6 divided by 3 would be 2. And then I have this cube root of PQ left over. All right, second one. Cube root of 64. What times itself 3 times gives you 64? Well, that's 4. And then times the cube root of PQ. Now this one maybe doesn't look as nice to you. It's not as decent of a number to deal with, but take a look at the radical here. Those are actually the same, right? They're both cube roots and they're both a p and a q. So we actually can combine their coefficients. Now here's the thing. When I combine their coefficients, I can't actually do the operation. I can't actually do that subtraction, but I can just write it as subtracted. So, I mean, normally I would normally do that operation. I can't now because they're not I don't know what P and Q are, but I can put them together at least. I'm writing it as what I would do once I know those. So because they're like terms, I can actually put them together even though the numbers aren't super great with that. So the variables do make it more complicated. That's just a harder thing for people to think about, but the goal is the same. We're trying to make that radical the same. All right, let's try some fractions here. So remember how we deal with those. So we're going to take a look at, again, simplifying and breaking down when we have a fraction situation. So definitely not like terms. We're going to try to simplify as best we can with both parts. So let's start with square root of 8. Biggest perfect square that divides into 8. Well, that would be 4. So that would be square root of 4 times square root of 2, which is 2 root 2. So being able just to simplify a regular, just kind of smaller number, what can I take the square root of, what can't I, biggest perfect square. Now remember how we handled the fractions? We treat the top and the bottom separately. So instead of thinking of it as a fraction trying to take the square root, we do the square root of the numerator and the denominator. Well, this makes life a whole lot easier because square root of 64 is just 8 and the square root of 16 is just 4. So 8 divided by 4 is 2. So I get 2 square root of 2 plus the whole number 2. Now let's take a look at that. One of them has a radical and one doesn't. Never going to be a like term, right? So if you have something with a radical and something that doesn't, it's kind of like the equivalent of saying 2x plus 2. I would never put those together, right? Because one of them has the x, the other one doesn't. This is exactly the same thing. So that's as far as we can go, but gosh, that looks better than what we started with, right? We always want to simplify as far as we can. All right, let's do the same kind of concept for letter B. I want to think of each of these as top and bottom, right? So I'm going to think of it as square root of 8 over square root of 9, and then plus square root of 18 over square root of 36. So let's see if we can separate them out to make this a little bit easier. For the first fraction, square root of 9 is just 3. That's pretty easy. For the second fraction, it's just a 6. Also pretty easy. Not too much to deal with there. But let's do the numerators. Square root of 8, it's not a perfect square, so I'm going to break it down just like I did in the last one. So what's the biggest perfect square that divides into 8? That would be 4. So 4 times 2. So the square root of 4 is 2. So we have 2 root 2 over 3. And then for our second one, 18. Also not a perfect square, but what's the biggest perfect square that divides into 18? So go up the list. 4 doesn't. How about 9? Ooh, 9 does. 9 times 2. So that would be 3 times the square root of 2. Now we have two fractions here. We have a couple ways we can go with this. 3 6 actually reduces because it's the whole number parts of the problem. I could actually reduce that down if I wanted to, and then I can simplify from there. Otherwise, I can just go right from here and try to put them together because I think these are like terms. Look at your radicals. We have a square root of 2 and a square root of 2. So they are like terms. Do you remember how we were able to add fractions together, that warm-up question? We needed a common denominator. So I think what I'm going to do is I'm going to go ahead and leave that second fraction because I think I can make a 3 into a 6. I think I can leave this one and be able to get this first fraction to have a common denominator. What do I multiply 3 by to get 6, to make that a sixth? Well, I'd multiply by 2. So I'm going to multiply the numerator by 2 as well. So 2 times 2 would be 4 square root of 2 over 6. So that same idea that we did for those warm-up questions works here as well. We just need to get a common denominator so we can add them together. So let's put them together. 4 of them plus 3 of them would give you 7 of them. So 7 square root of 2 over 6. So we could do the same idea with radicals that we would just with a regular fraction, which is kind of cool. Okay, we're going to finish up with another common denominator. Now this one, thankfully, they're already alike. So this is really similar to the one that we just did, right, when we put these together. They're already like terms. I didn't even have to simplify first. I just need to make a common denominator. And I think, again, 3 does divide into 6 evenly. So how about multiply by 2 again? So that would give me 4 square root of 5 over 6 plus 4 square root of 5 over 6. They're actually the same term. So I can add them together. So 4 plus 4 would be 8 square root of 5 over 6. Now, something that I was going to talk about in that last one that I will here, that's kind of like having 8x over 6. And I wouldn't want you to leave it that way because 8 6 can be reduced. I can divide each of these by a 2, right? So 8 divided by 2 would be 4. And then 6 divided by 2 would be 3. Well, this is no different. Think of radicals sort of like variables, right? It's a coefficient, 8 over 6, so I can divide that down to 4 square root of 5 over 3. And you can write it as a fraction like that, or some people write 4/3 times the square root of 5. That would be the same thing, whatever's more comfortable for you. But make sure you simplify or reduce at the end if you can. So dealing with adding and subtracting really boils down to simplify those radicals first. To be like radical terms, you have to have the same root, the index, and the same expression underneath, the radicand. And if they're the same, you can put them together. Just remember to simplify first.